In this video, I'm going to show you exactly what a BLDC refrigerator fan motor is, explain how it works, and then demonstrate it running right here on the test bench. These motors are everywhere in modern refrigerators, especially in evaporator and condenser fan applications. They're compact, energy efficient, long-lasting, and designed to operate reliably in harsh conditions inside the appliance. BLDC stands for Brushless Direct Current. These refrigerator fan motors are fully integrated units. The electronics in the motor are molded into one assembly. Inside, you've got a combination of technologies: a microcontroller, a three-phase driver circuit, Hall effect rotor position sensors, and the motor itself. All of it is sealed and built for years of operation. Here's a simplified block diagram of what's going on inside of a typical BLDC refrigerator fan motor. At the heart is a microcontroller. This chip takes in commands, reads feedback from the sensors, and generates the control signals to drive the motor. On the left, we have the PWM input. That's pulse width modulation. This is the pilot signal from the refrigerator's main control board. The duty cycle, or percentage of time that the signal is high, tells the motor what speed it should run. The microcontroller reads that pilot signal and then generates its own set of PWM drive signals. 3 of them, spaced 120 degrees apart. These go to the three-phase driver. The three-phase driver is a set of 6 power transistors arranged in what's called a three-phase bridge. This circuit converts the low-power control signals from the microcontroller into the high-current, precisely timed three-phase output that powers the motor windings. Inside the motor, Hall effect sensors detect the motor's position. That information is sent back to the microcontroller so that it can synchronize the drive signals and avoid fighting against the motor's own back EMF. Finally, the RPM output is fed back to the refrigerator's main control board. That allows the appliance to coordinate the fan's speed with cooling cycles, defrost modes, and energy efficiency routines. Power for the entire motor assembly comes from the 12-volt supply, shown at the top left of the diagram. On the bench, I have a variable DC power supply, a BLDC evaporator fan motor from a GE refrigerator, a signal generator to provide the PWM pilot signal, and an oscilloscope to monitor both the PWM input and RPM feedback output signals. Also monitoring the RPM output is this fluke meter set on frequency mode. This circuit here helps the signal generator drive the motor's PWM input. On this motor assembly, the red wire is the 12-volt input. The white wire is ground. The yellow wire is the PWM input from the signal generator. And the blue wire is the RPM feedback output signal. We'll start with a 25% duty cycle on the PWM input. You can see the fan spinning at a relatively low speed, and the oscilloscope shows a narrow high time on the PWM input signal. Now we'll increase the duty cycle to 50%. The on time of the PWM pulse doubles, and the fan speed increases accordingly. The RPM output signal also increases in frequency, matching the higher rotational speed. At 75% duty cycle, the PWM pulse rate is high for most of the cycle. The motor speeds up further, and again the RPM output frequency rises proportionally. Finally, here's 100% duty cycle. At this point, the PWM input is essentially a constant high signal of 12 volts. The same as directly connecting the PWM input to the power line. This motor runs at its maximum rated speed now. Now, just for fun, let's crank it back down to just a few percent. As you can see, the speed is just down to a crawl. There's no way you can get this kind of control with an AC motor, as the speed for an AC induction motor is tied to line frequency, whereas with this motor it is whatever the microcontroller drives it at. So to recap, a BLDC refrigerator fan motor is not just a motor, it's a complete electronic control system in a small sealed package. The PWM input tells it what speed to run. The microcontroller processes that command and generates a three-phase drive signal. The driver stage powers the motor windings, while Hall sensors keep everything synchronized. And the RPM output feeds back to the appliance's control board to coordinate cooling and efficiency. This design is more efficient, quieter, and longer lasting than traditional AC shaded pole fan motors. And it gives the appliance's control board precise control over airflow at all times. I hope this demonstration gave you a clear look at how BLDC refrigerator fan motors work. If you found it helpful, please like the video and subscribe to the channel for more practical electrical content. Thanks for watching.